Welcome. Today we're going to talk about attention. Attention is a mechanism within neural networks. It's a type of architecture, or a subpart of a neural network architecture, which was popularized recently due to applications involving sequence models. So it's now expanded beyond this, but it was really started due to sequence models. So just to remind you what sequence models are, they're when you have some sort of sequence of things. For example, like in applications like NLP or language modeling. So we've already talked a bit about sequence models, and in particular how to handle them using, say, RNNs. So let me just... So these are kind of what you would use for sequences before, say, 5 years ago. Yeah, attention really became popular around 2017, or at least that's when it was sort of popularized with a certain paper, which we'll get to. But before then, RNNs were really the thing that you would go to for sequence models. And let's talk about RNNs and see why they might be deficient. Why might they not be good enough for our purposes? Let's just look at a very simple sequence model, sort of or not a sequence model, but an RNN, a very shallow one, and just see what it looks like. So suppose this is our RNN, and what we have here are these are the hidden states. Each of these hidden states, we're going to say that these are each sort of d-dimensional hidden representation. So the representation dimension that we're going to use for the state here is d-dimensional. And let's say the length of the sequence is n. So let's try to understand what exactly the complexity and what are the costs of trying to do this type of language model. Well, first thing that we need to note is that each language model, what's the computational complexity of this? Well, the computation isn't too hard to see. What we're going to be doing is we're going to be doing a sequence of updates for each of these. So let's just focus on one update. So let's say the computation done here. So what we're going to be doing is computing a size d vector here, and it'll be based on the previous size d vector. So this would be a d by d, it would be a matrix vector product where, like, essentially it would be something like this. We would have h1, let's say, and this is h2, and we can say that h2 is equal to some nonlinear activation of some weight matrix times h1 plus maybe some other, let's say some other weight matrix times the input, would be like x2 or something. But the point is that the main computation we're going to be doing here at each step is going to be a matrix vector product. Let's just focus on this w times h1. That's going to be a matrix vector product where the matrix is size d by d times a size d vector. So the total computation that is required to compute, say, this product, and in fact the overall thing, is going to be O of d squared per update. And that's not too hard to see. Just think about how you do a d by d matrix times the length d vector. You'll say the computation is d squared per update. And then since there is n total length of the sequence, that means that the total computation required is O of n d squared computation. So you might be wondering, is this good or is this bad? Well, we're not going to worry too much about whether it's good or bad in like by itself. It's kind of hard to say. But the main thing that I'm going to note is not necessarily how big the compute is. It's the fact that this is not very parallelizable, in the sense that if you wanted to process an input of this sort, then you'd have to do the first computation, and then you do the second computation, which depends on the first computation. The third one depends on the second computation, and so on and so forth. So total, you have to do a sequence of n of these d squared computations, all in order, and you can't parallelize them. Maybe each of these d by d, matrix vector products you can parallelize, but if you want to do the computation, you want to compute, say, h sub n, then that really requires you to go through this long chain. So let's just say, like, the issue that I'll highlight is that it's not easily parallelizable. And it's an inherently sequential procedure. And the way that we might quantify that is looking at the longest length chain in this. I'm not going to formally define what I mean by that, but you can see that if you want to compute hn, then you can see that you have to go through a chain of length n in order to get to, compute. There's a sequence of n computations you have to compute in order to compute hn. So longest, we'll say the longest path, and I'm not going to formally define that, but hopefully intuitively it's clear what I mean by this, is O of n in length. So that's bad for this parallelization, and also it'll have some issues when we're doing optimization, because you can see that in order for information to, this is again informal, but for information to propagate from the first input to the to this last symbol, essentially that has to go a very long path. So I'll just say vaguely some challenges in optimization. And the idea behind attention is it's going to be a method. It's going to be a different type of architecture, different setup for doing these types of computations, which will make things essentially very parallelizable, and therefore it'll alleviate these issues. It'll get rid of this longest path problem that I mentioned here, and let us do things in parallel, and that'll allow us to scale things up a lot. I mean a lot. We'll see what we mean by that towards the end of this lecture. Okay, so the key thing that we're going to look at is what is known as the the key terms here that you need to know is there is the attention mechanism. And this is kind of like the attention mechanism is kind of like a type of layer. So we'll get to more precisely what that is. But it's part of what is known more broadly as an architecture known as the transformer architecture. And this is relatively recent in the sense that it was introduced and attention was really popularized in this paper by Vaswani et al. In 2017. And let me show you a screenshot from their paper. So this is what a transformer looks like. So this is an important picture, so we're going to keep revisiting throughout this lecture because there's a lot of different pieces here. But I'm going to try to explain all these different pieces as best I can, and hopefully by the end you'll kind of get what this picture is supposed to say. So hopefully this is visible. Yeah. So this is what is known as a transformer architecture. Let me try to walk you through and explain different parts of it, and then we'll go through them each in more detail. So the important things to note are first of all, this is going to be used for supervised learning. First of all, later on we'll talk about how to get beyond this, but you can picture it as a sequence to sequence type task where there's going to be a sequence of inputs and a sequence of the inputs are a sequence and the outputs are a sequence. So yeah, those will be kind of important things because it's a supervised task. And you can see, roughly speaking, the architecture here is divided in two parts. If you draw a line down the center, we didn't really talk about it too much. We mentioned it a bit earlier, but this can be divided into what's known as an encoder-decoder setup. And you can see that this half is the encoder. You can see that this takes the inputs and it encodes them. And somehow the right-hand side is going to be the decoder, where it's going to perform a type of decoding in order to get the answers. Okay, so that is the architecture. What are the different things that I should comment here? Yeah, like let me just sort of give you at a very high level what's going to go on here. We're going to start with the inputs. What's going to happen next to the inputs is we're going to take these inputs, which are maybe just like a sentence. Imagine as a canonical task, you can picture, say, next word prediction as a reasonable thing, or you can think translation from one language to another. So you can think of the inputs as being a sequence of words, and then the outputs will be another sequence of words. So one way to picture this is what'll you do? So the first step is first just get an input, which is a bunch of words. And what this input embedding and positional encoding will do is it's going to take your input and convert it from words to something which is more mathematically convenient for doing neural network operations. So you can think of this as sort of like a kind of encoding of the words into vectors. And then what'll happen is this we'll have this multi-head attention. Attention, of course, the key part of today's lecture, which will do some sort of transformations, which we'll talk about. And then we do pretty typical neural network things like just feed forward networks and stuff like that. And then we repeat it several times. You'll note this NX here. So basically, we're going to repeatedly do this attention procedure and then some neural network operations many, many times in a row. And then what will happen is after you've done these operations, you'll spit out a context. Now, this context, that will go into the decoder. And the decoder is very similar in the sense that it's going to encode the output string, which should be coming up, and it's going to run it through a number of very similar steps. There's going to be different types of attention that we're going to use here. This one's going to be masked, whatever that means. And you can see that this is self-attention, whereas this is attention with a context. We'll talk about these various differences, but really it's just the same sort of thing. We feed the output into this network and we do a bunch of operations repeatedly, and you do it a bunch of times. Eventually, when you're done, you'll get some output set of vectors, and then you're just going to run it through a linear layer and softmax it to get outputs. So that's at a high level what's going on in a transformer. But let's take it a little bit slower and walk through these one by one. So the first part is that we're going to talk about is this sort of like part here. Let me just sort of highlight the fact that we're going to really talk about how to go from a word or a sentence, let's say, into a mathematical representation of our data, which is going to be more convenient. So we're going to revisit this picture a bunch of times, so keep it in mind. But yeah, for now, just picture this bottom part here involving this input embedding and positional encodings. Okay, so I'm going to only describe it for the input, but it's really the exact same thing for both the input and output encoding. So what is the input that we're going to start with? The input we're going to start with is going to be something like the following: x1 through xn, and let's just transpose it for simplicity. This overall thing will be in, say, r to the n by p, where xi is in r to the p. Okay, let me explain what I've got here and what I mean. Let me just say one last thing. This will be a one-hot encoding. So, okay, what is this? We're just saying that the input will be a sequence of length n, because we have x1 through xn. Each of these vectors is going to be one of the words in our sentence, let's say. So let me just sort of specialize for this, that each input and output is going to be, each input is really going to be a sentence, which we want to do something with, and each of these xi's is going to be a word or a representation of a word. Like I said, these can be applied in more different contexts, but for today's lecture, we're just going to focus on sentences and words so that we keep it simple. So yeah, it's going to give you some sort of matrix where there's n rows. Each one is going to represent a word, a word, one token, and each row is going to be of dimension p, where p is some number which represents the size of our vocabulary. In particular, each of these rows is going to be a one-hot encoding of the word. So like, just to give you an example what I mean by that, we've already talked about one-hot encoding, but suppose we have the sentence which is like the quick brown fox. Well, what would this look like in sort of this input format that we have here, where we do this one-hot encoding? Well, what it would look like is it would be a bunch of vectors which are kind of like this, where you can see we have a 1 in exactly one place and 0 everywhere else, where the location of the 1 tells us which word we're looking at. And you can see that these are all 4 different words, so we have different locations of the one. And you can see these are very sparse vectors. So okay, I just let p equals 7 for this example. I just wrote these as 7-dimensional vectors, but really you would have p being the size of your vocabulary. In particular, p is probably going to be something in the tens of thousands generally. So you're going to have a bunch of your input. You're going to first map it to these one-hot vectors, which are very large vectors, which are very, very sparse with just a single one entry. So perhaps, obviously, maybe not obviously, that this is not a great way to represent words just because it's convenient for just feeding in. But when we start doing neural network operations, these are very big vectors, they're very high dimensional, and there's not really a good reason for that, in the sense that these are they don't really need to be this high dimensional in terms of their representation. It's kind of making it expensive for no good reason in terms of dimensionality. So what we're going to do is use what's known as a word embedding, or in particular, we're going to actually learn a word embedding. So we're going to find some mapping from the set of one-hot vectors, which are high dimensional, into non-sparse vectors, which are lower dimensional. So let me write it like this. We're just going to say there's an embedding. And this will allow us to find a better representation of these words. So we can just think of it as x, where this is this whole vector x. This is all of these inputs. This is going to be the whole matrix. And then we can do x times we, where this is our, this is going to be a learned embedding matrix. So that's right. This is going to be learned, and by that I mean this is just going to be a vector full, or a matrix full of parameters. So let's just see what dimensionalities we have here. So this x is going to be, like we already said, this is going to be in r to the n times p, and this w sub e is going to be r sub r to the p by d. So then overall, this matrix product, this is going to give us something which is in r to the n by d. So okay, let's see what we mean by this. The idea is that originally we had something which was n rows, where n rows, each one corresponds to one token or one word, and p columns. And now we've got something which is n rows. Again, each row will correspond to one token, but this time we only have d columns, where in general we take like d to be much, much less than p. For example, like I said, p would be in the tens of thousands, whereas d, think of d something more like maybe 512 is a common one, and I think that might be what they use for this paper by Vaswani et al., for example. So yeah, this can be like much smaller. Yeah, it's a type of dimension reduction operation in order to make this more informative. Okay, so that's the first thing we do, where we convert from these like very sparse vectors and sparse and high dimensional vectors to lower dimensional vectors which are not sparse, and this will be convenient. Okay, so that's the first thing we do. The second thing we do, we can see, let's return back to this picture we have here. We can see the second thing we do is this weird positional encoding, whatever that means. Let's explain what that means, and let me try to motivate what this positional encoding will do. Let me give you an example of a sentence first, or two sentences. The dog is behind the cat. And the cat is behind the dog. So you can see that these two sentences, they have not very different meanings, but they have different meanings, even though they have the exact same words in them, right? So this is kind of, yeah, the idea is that when we're going to be processing these words, or sorry, these two sentences, we're going to somehow need to remember which order the words are in. This is done automatically when we're looking at an RNN, remember? Because things that they go in a line, in the sense that you process the first word first, and then you process the second word, and so on and so on. So somehow when you're working with an RNN, you're definitely explicitly, maybe implicitly, using the positions of the words, where things that come earlier in the sentence are processed before things later in the sentence. So it has that information here. We haven't said exactly what attention is going to be yet, but in attention, I'm going to claim that that information is somehow lost if you don't take care to actually include it. So let's make sure we include it. And the way we're going to do that is essentially based on where. So we have the sequence of vectors that we converted to, and then remember we map this through the embeddings, but we're going to have a sequence of vectors, each of one refers to, sorry, let me just add this transpose. Each word is going to be a vector in this. So what we're going to do is actually add something to each vector in the sequence in order to encode the value of where it is in the sequence. For example, a very simple, like a simple and naive thing you could do is, for example, add on to the first thing here, you add on a 0, and then the second thing you add on a 1, and you add on a 2 for the next thing, and so on. And by adding these things, that somehow indicates where, adding these to or maybe you have a vector full of 0s and a vector full of 1s and vector full of 2s, and you add that on to the embedding. And you can see that, okay, you've sort of added something to each different vector based on its position, and so that somehow carries the information. For example, in the first sentence, you'll add a vector of, say, 2s to the dog one, to the dog symbol, and a vector full of 6s to the cat one, and vice versa in the second sentence, so somehow they're going to be kind of different. But this is a very naive way of doing it. But it's at least the vague idea that we're going to add something to each vector based on its position in order to somehow encode that position. And I'm not going to get into why this is the right thing, but what we're going to do is we're going to construct v in r to the n by d. So note that this is the exact same size as our resulting embeddings of the input. It'll be something like this. And what actually, there's a few ways to do this. There's two options, really. One thing you can do is, you can use fixed embeddings. Or sorry, fixed encodings for the position. Use fixed positional encodings. And the one that they mentioned in this paper is something like the following. It'll look kind of complicated, but let me just write it here. So you can see this here, where I is equal to 0 to d over 2 minus 1. So this looks kind of weird, and I'm not going to get into it, but you can look at it carefully and see that essentially it adds some weird sinusoidal matrix to this, which is kind of periodic in some way. And yeah, this will kind of somehow encode where a word is in the string, in the sequence, because you can see that the earlier words, they have they have smaller t's, and therefore they'll have values based on the sinusoid based on that. But as we proceed through this through the sequence, we're going to add values of sine and cos with larger t's. So either way, that's don't worry too much about the specific details of these vectors. The point is just something which encodes the position. But the other option is, instead of a fixed one, is just like everything we do in machine learning, learn the best, like learn a v. So this can be just some parameter that you learn, some matrix that you learn, and then just optimize it the same as we do with everything else. So, okay, the point is that we'll get this matrix v, which is an Rn times d, and then we're just going to add it to the embedding. And that'll give us something like x times we plus v, which is going to be a matrix with r to the n by d. So n rows, again, where each row represents one token or word, and d will be the dimensionality of each representation. So yeah, that's kind of the first part of these, both of these input and output encodings, I guess. That's what we're going to do first, and then we're going to start feeding it into these actual main layers of the network. And now we're finally going to introduce attention. In particular, we're going to talk about self-attention, which is what's exactly used here. The simplest type of attention is this little component right here. Okay, let me grab the picture of what attention is sometimes looks like. Especially, there's another figure from the paper by Vaswani et al. We'll just keep it here to sort of see. This is more general than what we are going to be looking at for now. We'll look at a sort of more complex version which matches up with this. But for now, we're going to look at self-attention, where just kind of matching up with this picture, you can see that, oh, whoops, I got the pages in the wrong order. All right, that's probably good. But all right, you can see in this picture on the first page that, notice there's 3 inputs to this attention, and they're all the same thing, it looks like. So that's why it's called self-attention. So let's return to this picture. You can see, I haven't explained what this means yet, but we're going to talk about that. But what self-attention means, self-attention, that means we're going to essentially feed the same thing into all things, into all 3 of these inputs. There's generalizations where you can put other things in there, but we'll get to that in the appropriate time. So, okay, with self-attention, is going to be the following. So given, at least for our setting, this is what the first thing we're going to pass our resulting matrix in, which is our n times d. This is what we're going to put it into. So given, say, matrix V, which is in R n by d. Just to be clear, I guess I use the same letter. Don't get confused with this this V here. My bad. Yeah, the positional encoding is different from this, but think about V as the output of this computation right here. Okay, but given some matrix like this, we want to compute the following. We're going to update V to be the following quantity. This is the operation we do, which looks a bit intimidating, but let me explain what each of these things are. So let's first look at this thing, this lambda. This is actually going to be a type of hyperparameter. It's called the scaling factor. And I think you often set this to like a factor of, set this to equal like square root d. But at least for the sake of intuition, or when we're discussing this, we're going to basically ignore this factor and pretend it's a 1, just because it's not really too important in terms of what's really going on. To really understand what's going on, you just have to focus on the other things. So again, just pretend lambda equals 1 for the sake of discussion. Okay, so then what are we doing here? The main thing you can see here is, first of all, there's kind of 3 steps here. What you do is you first take a matrix outer product with itself. Second thing you do is you take a softmax of the result over the rows, and then you multiply that by the original matrix that you had. Now that's 3 things, and maybe none of them made sense. So let me explain them one by one. Oh yeah, and one thing I want to make sure that's clear here, by the way, is this attention mechanism. It actually doesn't have any actual learnable parameters. You can see this is just an operation. It's there's a hyperparameter maybe, but really there's no parameters when you're doing this itself. You'll maybe have parameters and layers which feed into it or go out of it, but this is a parameter-less thing. It's just a transformation. So let's try to understand what each of them is. Let's first look at this multiplication, v times v transpose. And let's take a look. Let me try to draw a picture of what this looks like. So this is the matrix V, which has, what is it? It's in the first word, the first row is the first word, the second word, and so on. Where, remember, each of these rows is going to be a d by d, or sorry, a vector, a length d representation of it. And I can't really write sideways, but let me try my best. Word 1, dot, 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 and then at the end we have word n. So this is what v times v transpose looks like in terms of a matrix product. And so we just take this matrix product, matrix product, and that'll give us a result which looks like this. It's going to be a result which is, this is going to be in R n by n. And what is each entry going to be? So let's focus on a single entry of this. So entry ij. The idea of what entry ij of this matrix VV transpose is going to represent is it's going to represent how similar word I is to word j. Now, why is that? It's kind of just like the dot product is a usual measure of similarity of two different words. And so taking the dot product of two vectors will tell you how similar they are. So let me just write this. This is going to be dot product of word I and j reps, or the representations. And so the idea is, just vaguely speaking, if I and j similar, if they're similar words, whatever similar means, because it's not really clear, this is a vague informal term, but we'll demonstrate with some pictures what happens in practice. But if they're similar, there'll be a large value. And if they're different, there'll be a small value. So yeah, importantly, we'll also note that this encoding also contains position. So it's not just strictly going to, remember, we added on this positional encoding. So this matrix won't only contain what the words are, but it'll also keep track of where exactly the words in the sequence appear. So somehow accounting for all this information, then this entry will tell us whether words I and j are somehow similar or related. So that's exactly what this matrix was going to be. It's just going to be a sort of pairwise for each pair of words, tell us how similar or different the network thinks they should be. So that's the first step, which is I think pretty intuitive. Find out which words are similar to each other, or which words are related to each other. This seems kind of natural in the sense that, for example, in this sentence, we're going to want to know what object is behind what, and so maybe both, I guess behind might have a high attention, a high score here with respect to both the dog and the cat, and vice versa, and same in this one as well. But it's really going to try to discover which words are related to each other. Okay, so that's the main thing that's going on in that sense. Now let's take a look at what we do given this matrix of similarities. Well, the first thing we do is we take this row-wise softmax. So it might not be clear what I mean by softmax when we're applying it to a matrix, but we're going to make it into a row-wise operation. So what'll that do? So that'll essentially make it so that each row is a probability distribution. And maybe a probability distribution might not be the best way to think about it. Another way of thinking about it is just a set of weights which add up to 1. So it's kind of a reweighting or a different way of averaging the rows, because that's exactly what we're going to do. We're going to, sorry, yeah, it's a bunch of weights which add up to 1. and that'll tell us, that'll be useful interpretation. So, okay, yeah, now we've done this operation where we computed how similar each pair of words are, and then we normalized each row in some way using the softmax operation, not just like a naive averaging, but the softmax averaging. And then the last thing we do is we multiply it by v. So let me just recall, we just do softmax v transpose, and then we multiply that by v. And let's look at the size of this. So this is just so that we're on the same page by what size things we're looking at. So like I said, this is Rn by n, and this is going to be Rn by d. And then the overall product is going to be, this product is going to be equals to Rn by d. So it's essentially going to be the same size as the v that we put into this overall thing. Remember, this just takes a v and spits something out. It's going to be pretty much the exact same size as we had going in, but it's somehow going to be, my claim is that we took the v and we replaced each row of v by a weighted combination of the other rows. So that's essentially what this type of operation does here. Let me be a bit clear about, let me try to be clear or give you an example of what this does. So like, let me just say here that replace each row of v by weighted sum of rows. Now let me illustrate just with a very simple example. This is kind of a bit of a character that probably might not come up in a real network, but say our matrix here, softmax v transpose, this could look something like this. Maybe 2/3, 1/3, 1/4, 3/4. So this might be what this looks like. Note that importantly, since we ran some sort of softmax operation, each row is normalized. That makes it so that each row is a probability distribution. And maybe our matrix V is going to be 1, 1, 0, 0, 0, 0, 1, 1. So this isn't strictly true because like if you compute the softmax of this VV transpose, it's not going to be equal to this, but just pretend we've done this computation and it gives us some matrix here and some matrix here. I just want to focus on what this last softmax times V is going to do. It's basically going to, like I said, replace each vector by, or each row of this matrix by a weighted sum of the other rows. And so it'll just become something like 2/3, 2/3, 1/3, 1/3. And here we have 1/4, 1/4, 3/4, 3/4. So that is an example of what this type of thing does. Yeah, so that is, in a nutshell, what the self-attention mechanism is. It just, yeah, takes in a matrix, and then it'll do this type of transformation, which does a reweighting of the rows, or it replaces each row with a sum of the weighted sum of the rows, which kind of represent how important various things are to each other. So the really neat thing to note about this all is the following fact, that this was actually just, this can all be easily parallelized. Actually, we'll talk about that in a sec. First of all, you might be wondering, how should you visualize attention and what is it really doing? There's a very nice blog post from which is associated with this paper, and this is maybe how you can picture what attention looks like. So let's see what this means. So this is basically looking at the attention mechanism activation for this word "it" in the sentence, "the animal didn't cross the street because it was too tired." So when you read the sentence, what does "it" refer to? Well, it probably refers to animal because it was too tired. The animal was tired. So you can see, therefore, that the word "it" here, that points to animal. That's sort of where the heaviest value is, and that kind of represents, I think, the row of in this sort of softmax VV transpose, where which corresponds to "it." So this would be, say, the 8th row of this softmax VV transpose matrix. However, if we change the sentence to be the animal didn't cross the street because it was too wide, you can see that in this when you read it, it refers to street. And indeed, if you compute the activation for the attention mechanism sufficiently deep in the network, so it's kind of figuring stuff out, it's actually learning in the later levels, you can see that it now points to street. So it kind of has learned, based on these activations, that it refers to animal here, and it refers to street here just as a human would. So that's kind of how you can visualize attention, this self-attention mechanism, really picking out which words each word could be related to. And this picture, I think, illustrates it very well. Cool. So let's talk about the complexity here and how this is how this compares with RNNs. So the nice thing, like I mentioned, is the fact that what is attention here? When you think about attention, what is it? It's just a matrix multiplication, and then you do the softmax, and then you do another matrix multiplication. So it's really just basically a pair of matrix multiplications, which I'll claim matrix multiplications are easily parallelizable on a GPU. If you compare this to an RNN, remember an RNN was very non-parallelizable. It's going to be a very long sequence of things, which you have to do in sequence, and you can't split up on GPU. So let me say that the computation I'm going to claim that this is O of n squared by d. And where does this come from? Well, this is not too hard to see because when we do VV transpose, this is multiplying a n by n, or sorry, an n by d matrix times a d by n matrix. So the overall running time is O of n squared d for this. And then also when we do the softmax of VV transpose times V, this is also going to be an n by n matrix times an n by d matrix, so this is going to be also O of n squared d. So just double check these yourself, but you can see that the overall computation is n squared d. Let's compare this with RNNs. That was O of n d squared. So first of all, just in terms of pure running time, you can see that this is different in the sense that this has a factor of d and this has a factor of n. Which one is better? Well, typically n is going to be much, much less than d. You can see this, for example, in our simple examples where for these examples here, like the n is going to be the length of the sentence, which is maybe like a couple dozen. Whereas for d, the dimensionality of the representations, those could be in the hundreds or maybe even thousands. So you can see that this is going to be a couple orders of magnitude less than d often, and therefore it's going to be generally much faster, except when we start making the sequence length very long. That's one advantage, so it's faster, but also remember the key thing, which is the fact that the max path length is much shorter. So before, when we were looking at the RNN, we really saw that things have to go sequentially, and you go through all these different layers in order to get info from the beginning to the end, and it all had to be done sequentially. The nice thing when we're doing this attention is the fact that for every word in the sequence, we kind of compute their relationships to each other without having to go through any sequential procedure. So that means multiple things. One, this helps again with the parallelization, like I said. You can just do this all on the GPU and compute it very quickly. And additionally, there's the fact that you don't really have to worry about information propagating through many different layers. You can immediately just look at word 1 and word n and how they're related, and that'll give you things without having to wait for the information to flow, which helps with optimization. So let me just summarize that by saying there's a shorter max path length, which is advantageous for both parallelization and running time. It'll be sort of like O of 1. Okay, so that is kind of the idea of attention. Now, the next concept that we need to do is basically multi-headed attention, which is not really that much different. And you can see this kind of in this picture here, right here. it's basically the same thing as before. You can see that the scale dot product attention is essentially what we were doing before. But the idea is, instead of doing just one thing, you do H of them at the same time. So if you want to think about what I mean by that, remember when we were doing CNNs, you'll recall that we had many different filters. We had many different filters because they would learn different features, each of them, even though they were kind of they all could do the same thing, but they all learn to do different things because that's just kind of how this system decides to optimize. Now, at the same time, that's kind of what we're doing with multi-headed attention. We're going to have different, we're going to be doing essentially the same thing in parallel, and each of them will learn to learn different things. So let me just write some pseudocode here. So what we're going to choose is some hyperparameter h, which is going to be how many different things we run in parallel. I think the original paper used h equals 8. But what we're going to do is for I equals 1 to h, what we're going to do is we're going to sort of split our input. Sorry, let me just write this. This is going to be v times w I. So we're going to essentially take our the input that we would have fed in, but now what we're going to do is we're going to multiply it by a dimension reduction matrix. So this is going to be r d by d over h. So the idea is we're going to reduce it from like d to, if h equals a, d to d over 8. So we're going to kind of scale things down. And the reason why we do this is kind of to reduce the number of parameters so things don't blow up too much. It'll also note that this weight vector w here will also be another learned weight matrix that we're going to figure out. And then what we do is we just do the self-attention on the resulting thing here. Times vi. And then once we've done that for all of these different parallel attention heads of the attention, all we do is we concatenate them and then we scale them back up. So what we do is we let v becomes concatenation of v1 through vk, or vh rather. So remember, these are all just going to be n by, say, d over 8 size matrices. So we're just going to horizontally concatenate them, and then we're going to multiply by w, where w is another learned parameter, where this is in r d by d. So it's just another parameter vector, a linear layer. So, okay, that's multi-headed attention. It's really just do the same thing, but split it up so that, and try to learn multiple different things in parallel, playing the same type of role that filters have in CNNs. Okay, so that's basically almost all of the encoders. So let's take a look at the encoder and see where we're at so far. You'll see that we have the input embedding, and then the positional encoding, all this, which is just preparing our input. Then we can feed it into this multi-headed attention. We said it's going to be self-attention, but with multiple heads, so we do it many times in parallel. And then what's going to happen? Well, we're going to do an add and norm. So this is kind of like this is going to be, first of all, you can see here we have a residual layer. Remember from our talks in CNNs that the residual layer allows the input to skip whatever layer we have. So that's going to be a helpful thing. We're going to have a residual layer as well as a norm layer that is something like layer norm in particular. So these are just going to be simple transformations. You can recall what residual layers and layer norm do. But okay, we do that. And then we're going to do another, just a basic feed forward layer. So this is not that complicated. Let me just let me write down. You know feed forward layers pretty well at this point, but let me just write a few things. Other details. So what we have is residuals, layer norm, But okay, let's talk briefly about this feed forward network. There's just really a layer. It's not really too much. So what we're going to do is we're going to have some n of a vector v. This will just be the following: w2 times relu of w1 times v. So hopefully this is basically familiar to you. This is just going to be a very simple network, which like is 2 layers. Let me draw a picture of it, maybe something like this, and we're going to have a middle bigger layer, and same back to the same layer, and then this just fully connected. Let's say similarly on this side, like this. So this is representing this, and the idea is that we apply this transformation. It just takes in a single vector, but recall that the output from our attention is going to be a matrix. So what we do is we apply this feed forward network to each row of the resulting matrix. So we apply it independently to each row of this matrix, which is kind of applying it to each token or each word in the sequence, maybe now a transformed word, and that'll be what we do. And in particular, the important thing is to mention that this W1 and W2 that we have here, these are shared across positions. So the first row and the 10th row and the nth row, they all use the exact same parameters, W1 and W2 here. Cool. So that at this point, we have gone through the entire left half of the architecture. So let me just walk through it again, just to make sure we understand it. We start with the input, which will be a set of 1 hot vectors. We're going to do this encoding to reduce the dimension and make it into less sparse, more dense matrices, or more dense vectors. We're going to add on a positional encoding in order to make sure that we encode the position information. Then what we're going to do is we're going to feed it into these encoder layers, where each encoder layer is going to be first this multi-headed self-attention, as we discussed. Then we're going to do a residual and layer norm, and then we feed that into a feed-forward network. Then we do a residual and a layer norm. And the idea is, you can see this nx here. Well, that means that we're going to do this many, many times. So I think in the original paper, they do 6 repetitions of this. So it shows this line going out, but really you should picture it goes out, and then you go into another one of these, and another one of these, and you go through 6 of them. But eventually, once you've gone through many of these encoder layers here, or encoder like gadgets that we have here, then eventually at the end, once you've reached the end of it, you're going to output a context vector. So this right here is the context. And that is going to be fed into the decoder. Now the decoder is what we're going to talk about next, which is actually, you'll see that it's pretty similar to the encoder. There's just a few little tweaks in terms of what we do here. And the main tweaks you'll see, I'll just point them out, just so that I prompt you. The differences are going to be the fact that we have word masked here. We'll talk about what that means. And also you'll note how the inputs here, these are all self-attention. Well, you'll note that these arrows here are not all the same thing. So these inputs here will be the context rather than the same vector here. Okay, so let's talk about the decoder and the various different parts of that. And the first thing we'll talk about is masked self-attention. Now, the main key thing is the idea in the following. Remember that when we're talking about when we're talking about the decoder, what we're looking at is the output that we're trying to predict. So when you're doing an output, you can't predict something based on what happens in the future elements of the output. Think of say, just to give you a simple example, suppose you're trying to do next word prediction. Well, when you're doing next word prediction, you can't look at the next word, because if you looked at the next word, then you'd be able to see, okay, that's obviously the thing that we should output, and that would be way too easy. So in some sense, we need to make sure that attention does not look at things which are in the future. And that's where the masking comes in. So let me just, it's going to be pretty similar to what we did before, but the idea is the following. Suppose we're given, say, some q, which is in r to the n by d. We're going to compute. It's going to be something very similar to before with just one addition. So we're going to let q become softmax of, now here is the difference. We'll input this mask function, which we'll talk about. Q. So this is masked self-attention, and you note the only difference that we have here is the fact that we threw in this function mask here. So what is mask? Mask is going to be something like the following. So say mask of some function m at element ij. So this is just going to be a matrix. The mask of m is going to be a matrix of the exact same size, but this is going to be, the ijth entry is going to be equal to -infinity if I is less than j, and mij otherwise. So the idea is you just basically set something to -infinity if it would correspond to looking forward in time in terms of the output. So let me just give you a very simple example. Suppose you had the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, then the mask of this, of m, this would just be 1 -infinity, 4, 5. Something like this. So you can see that we're just setting things above the diagonal to be -infinity. And if you think about what happens when you do softmax of this operation here, and then you multiply it by q, what essentially that says is that the first row of the result is only going to be a linear combination of the first row of the original matrix. Similarly, the second row of this output matrix is going to be a linear combination of the first two rows of this matrix. The third row is going to be a linear combination of the first three rows here, and so on. So it kind of, like I said, the intuitive explanation is that a row of the output can only depend on things that came prior in time, because you can't cheat by looking forward in the output to predict things. And yeah, it just kind of encodes that. So hopefully that's relatively intuitive what we're trying to do there, and this is how we kind of do it more mathematically. And so that's one part of the decoder network. So that's masked multi-head attention. The last new component I really have to describe to you is this multi-head attention, which takes in the context rather than self-attention. So let's just discuss what exactly this means. And it actually goes back to this picture which I flashed here. Yeah, essentially I X'd it out because we're talking about self-attention, but the idea is essentially we're going to feed in the context for these two inputs, and then we just feed in the other input for the other input. So let me just be more precise by writing it here. So let's say that this is, I don't know what to call it, but attention with context, which just means with context. I'm just trying to distinguish this from self-attention. What we're going to do is say, given context V, which is from the encoder, and Q, and let's say matrix Q, which is from the decoder, then we're going to compute the following. We're going to compute, very similar to before, we're going to let Q become Q transpose V over lambda times V. And yeah, the idea here, maybe if I could give you an intuition, it's kind of just saying that, because really what you want the output to be, when you're doing computations, you really want to take the input and predict something based on the output. or sorry, you want to take the input and then predict the output. But all this is saying is that we're going to use the output to somehow help us, if it can help us, whatever we've seen in the past. So, for example, is next word prediction a good thing to use? Yeah, I mean, like, next word prediction kind of says, okay, let's use the words that we've seen in the past in order to help predict what the next words will be. So you can see this Q transpose here as kind of trying to say, okay, let's find out which parts of V we should look at, because V is really what's going to contain the answer to whatever task we're trying to do, because the input. But okay, that's sort of like my vague hand-wavy intuition. Really, more precisely, it's just you feed these matrices in, because that's what you do. But yeah, okay, so that essentially tells us the entire decoder as well, except for this last part here. So again, the idea is you just encode your output, and then you run it through several of these layers in a row, which consist of masked multi-head attention, then the attention on the context, and then you also do this feed forward operation, and then you go through, say, 6 layers of this. And then finally, when you're done a bunch of layers of that, then we're going to go through the familiar linear softmax layer, which we've sort of seen many times before. So let me just be clear what's going on here. We have a final softmax. Okay, so what we're going to do with this final softmax, remember that this whole time we were dealing with things in convert vectors, or our tokens, from R to the D. So we were dealing with R to the D here. But what we're going to do is this was our kind of representation dimension, but we're going to convert from R to D back to R to the P. So this was the original size of the vocabulary, and we're going to convert back to that because this could be very large, or sorry, not because it could be very large, because this is essentially going to be the number of different words in our vocabulary, which we're trying to really predict what's the probability that's each one. But really, yeah, you can think of it just like trying to predict the label of what the next output should be. Which word in the vocabulary is going to come next is one way to think about it. And so this gives us prediction sequence y hat, where, yeah, you can think of this as being our predictions for each element of the sequence. So it should be for 1 through yeah, this should be for, you should have a sort of vector of size p for each input, for each position 1 through, say, L, where L is the size of the output. So that's kind of how we convert to it. And what is the final optimization problem we look at? We're going to try to minimize the following. We sum over all examples. So we've only talked about one sequence, one pair of sequences maybe. So you're going to do this over all the examples in your data set. But then you sum from j equals 1 to L, and then you have minus y sub j times log of y hat sub j. Where, okay, I guess the way you can see this is essentially this is the true label of whatever it's going to be, whatever the true output is. And then this is going to be the probability you assign to whatever thing that's there. And the idea is you want to minimize this as usual. It's the usual cross entropy loss. Now you might be wondering, let me just sort of be a bit more precise here. This is the true jth output. And this right here is the probability assigned to that. This is the prediction, like, I don't know, the logit corresponding to, yeah, the logit corresponding to the true output. and that gives us a loss function, very, very similar to what we've seen before. The only like special thing is the fact that the y hat, once again, has a lot of work going into it, because if you're going to optimize it, that's really, this kind of contains all the parameters of the model. And in particular, that's what the minimization is going to be. This is a minimization over all params in the model. So that means, for example, all of these, okay, I didn't write all the matrices that play into it, but for example, these matrices and these linear layers that we have here, as well as these dimension reduction matrices and the rescaling back up, not rescaling up things, but yeah, all these linear combinations here, every single thing, including all of the embeddings. So there's a bunch of different matrices and a bunch of different parameters here, and it's just going to optimize over all of those. Pretty similar to what we've done otherwise. Like really, that's often how machine learning works. Just make everything you want to do a parameter and throw it into this optimization. That's what you do. So okay, that's essentially. I've told you enough details that if you read the paper, maybe you could reconstruct this. And in fact, I've linked from the website some code which actually implements this entire paper. So the question now you might be wondering is, does it work? And the answer is yes, actually, it's shockingly effective. These are some results from this paper by Vaswani et al. And you can see here the what we have here is a bunch of different models. So all of these are sort of prior works. And you can see the blue scores. These are, just think a bigger number, the better it is. And this is for some language translation tasks. So English to German and English to French. You can see this is all the prior work that's happened before. And then you can see that the transformer architecture manages to improve quite significantly on the previous works by 2 whole points, which is actually kind of sizable here. Similarly, English to French, it also has some improvements as well. So these are nice, but the additional thing, which is really, really cool, is you can see that how much smaller the training cost of these things is compared to how big it was before. So you can see that transformer big, if you want to do either of these, then it's going to be the same cost. But you can see that this is 2 orders of magnitude. So this is 100 times faster than doing this. It does, in both cases, better than this model, which takes 100 times longer to train. So that should immediately scream out that there's something that can be done here. Because what if you made something bigger, which took 100 times longer to train? Can you imagine how much better it would be then if you sort of normalize or sort of equalize the training cost? And that's sort of where we're going with this. The fact that this is much more efficient than the previous methods means that it leaves space for us to scale things up, which is where we're going to go. So okay, so far we've talked about the basic structure of transformers. Now, for the rest of this lecture, I'm going to talk about various different like examples of transformers and how good they do. So the first one I want to tell you about is GPT, or generative pre-training. That is GPT-1. So like I said, yeah, this stands for generative pre-training. And let me illustrate what the architecture looks like. So it looks a little bit different. So these are all called, so while the original thing is going to be, was the transformer architecture, all of these things are called transformers as well. Maybe a bit confusing. They're all kind of similar architectures, but they're a little bit different in their own ways. And the important thing about this is you can see this actually looks very similar to the decoder stack, but it doesn't actually have an encoder. So you can think of it just the decoder of the transformer that we've looked at before. You can see in particular that it had this masked multi-headed self-attention and the feed-forward layer. It in particular doesn't have this attention with context because there is no context from an encoder. So yeah, you can think of it as just masked multi-headed self-attention and feed forward, and let's repeat it. Instead of 6 times as before, we're going to do it 12 times. So yeah, that's it. The other thing we're going to note is that there's 2 things we do with the output. In the sense that you can, let me say that this is called generative pre-training for a reason, because generative is kind of one of the operating words here, where we're kind of going to train it to be a generative model here. Like, let me speak from a high level what's going to go on here. Vaguely what you can think about, and this is the current paradigm of all attention-based transformer models in natural language processing right now, is the first thing you do is you teach them the language, and then after you're done teaching them the language, then you teach them the specific task you want to do. So I'm just going to use English as a running example because this is kind of what it's used in most. But you're first going to try to just teach this language model, how do we do English? What is English like? Make it go through 12 grades worth of English classes, so it knows everything about like the language of English. And then once you have taught it what English is and the structure and all the important things, then you teach it how to do a specific thing, a specific task in English. For example, you can teach it how to predict the answer to multiple choice questions, or like classification of some text or something. But yeah, the point is that it's first and foremost a generative process, and then we specialize it. So let me that's why we have kind of two outputs here, because this part is going to be used for when we're doing this generative pre-training as the name suggests, and then the other output is going to be used for when we're doing actual classification. So let me say the two stages of training. So one is unsupervised pre-training. And basically unsupervised here means, of course, there's no labels, but what this means is I just want you to find as much text as you can find, sentences, plain English sentences, as many as you can find, and just throw it into this. And what we're going to do is we're going to have the model try to learn English as well as it can from this. So the fortunate thing about text, English text, is that there's tons of it. You know, people have written thousands, millions and millions of books. There's millions and billions of messages sent online, which are publicly available. And just by scraping the internet, you can just use lots of text used, and that's it. Just plain English text, which has been generated and exists. And the type of, given this input, that's going to be all of our input to this. What we're going to do is we're going to optimize the following objective, which is basically the next word prediction task. And that's going to kind of be our proxy for how well it knows English. That is, if you're given if you can predict what the next word in the sentences comes really well, then in fact you can kind of say that you know English. Maybe not, but at least that's the sort of metaphor that I'm going to use. So we're going to say minimize over theta, sum over all examples, and then we're going to sum over I equals 1 to n, where n is the length of the sequence, the minus log of p theta of xi given x1 through I minus 1. So this is kind of what we've seen this before, but basically this is the probability the model assigns to xi, which is the ith symbol in the sequence, and then you do that conditioned on seeing what all the previous things are. The idea is if you optimize so that this is just, if you think about this as optimizing and trying to guess as well as possible the next word for each thing. So that's essentially what the unsupervised pre-training is, and training. And typically this is done for you in the sense that I don't know about GPT in particular, but generally it's possible to download language models from the internet right now, which have already had this unsupervised pre-training done, because this is not specific to whatever task you want to do. It kind of already knows English and it's ready to go. The next thing you do is supervise. And let me just draw in this picture here. That's kind of saying that ignore this part for now. Just don't worry about this text classifier when you're doing this unsupervised pre-training. Just sort of do this task here, where this is kind of just the prediction task. Okay, but in the second part, what we're going to do is supervised fine-tuning. And what this means is, suppose you want to do some sort of classification task. What you will do is you will essentially, once you've already done this pre-training, you've got a bunch of weights here. What you're going to do is then start with the weights that you get from doing this pre-training, and then you continue training from those weights, except you train a new objective which tries to optimize this task. So let me show you what I mean. So first of all, let's put a W here. W will be kind of some parameters which correspond to this task classifier here. So we're going to have some sort of smaller labeled data set that we're going to use for this, but we're going to do the following. We're going to minimize all the previous parameters of the model plus the model parameters here. And again, we're going to do all of our examples. We're going to sum over all of our examples. And then we're going to have two terms in our loss here. So the first one is the new loss, where this is kind of the classification loss. Y given, I guess it's P, Y of theta, and W, Y given X. Yeah, that's basically saying make sure it does well on this classification thing here. And then what we also do is we add in, basically we try to optimize this again with some new hyperparameters. So lambda is different from a previous hyperparameter, but also we try to do this as well. So you can see that essentially we're trying to optimize both the classification thing, but it also helps if we still try to keep improving the ability at predicting the next word, because maybe there's been some distribution shift in terms of what our specialized tasks are. So just to give you a sort of example that comes to mind is, suppose you first just do unsupervised pre-training on the overall data set, and then your supervised fine-tuning. Suppose the specific task you care about is you have some doctor's observations, like they've looked at the patients and they've written down what type of symptoms they have, and then based on that those symptoms, you want to predict what type of diagnosis you should give the patient. So you can see that this is a classification task, whether you say predict that they have cancer or not cancer. That's where you optimize here. But also, I'll mention that while these are written in sort of plain English, there's also, it's a little bit different from most of the text you're going to see. Like we have lots of English which is written on the internet, but it's not all going to be medical diagnoses. So somehow you have to also train the model in order to learn what a medical diagnosis text looks like, so that it becomes more suited to that. So that's kind of why we use both objectives here. But yeah, this is kind of the important paradigm nowadays in natural language processing, where really this is the thing you should remember, that you can get these big unsupervised pre-trained big pre-trained models, which are good in general. They kind of know the language, but then you can do a much cheaper and faster fine-tuning, which with much less data, which will get you good answers on whatever task you care about. Okay, so that is, what tasks do we care about? Let me show you a few examples of how we would actually use this to do something useful. So these are a few different examples as to what you could do with with GPT-1. So some of the things you can do are, for example, classification, where it's just exactly what we talked about here. Just feed it into this transformer, and then you put a linear layer on the end, and then it'll do some sort of prediction. You can also do various other things. For example, if you have some text, say text 1 and text 2, you want to see, for example, if they mean the same thing, the similarity between the two texts, then you can feed it in to a transformer, and then maybe sometimes you flip it, text 2, text 1, in case the order somehow is sensitive, but you can just do both, and then you add together, and then you can see how the similarity between the two are. Kind of another thing. And also it can answer multiple choice questions. This is kind of interesting because you kind of break it into multiple different prediction tasks, like yes or no answers. So you just have context in the potential answer 1, and you see how likely that is, and then you do context answer 2, and it'll see how likely that is. And overall, given all these different things, which are sort of binary predictions, it'll tell you, you can combine these in an appropriate way in order to find out which one is the right answer out of all of them. So yeah, just things like that. You can see how this is a fairly flexible core tool, which can be used to do many different operations. Cool. That's GPT. I'm going to talk about another architecture which is popular now, and that is the one known as BERT. I can't honestly remember off the top of my head what BERT stands for, bidirectional something something, maybe transformers. But the point is, this is just another type of architecture which is similar, which also fits into the general transformer framework, but looks kind of different. And let me kind of show you this picture here. So this might look a little bit weird, but let me try to first of all tell you sort of the key thing you should know is that before, while GPT used the decoder part of it, the BERT architecture just uses the encoder part. So you just chop it off here. This part becomes GPT. This part becomes BERT. Yeah, we'll focus on basically just this part for BERT. And yeah, kind of a way, if you compress that a bit, it looks kind of like this. So you can see this is the input here, and what we get instead of having just a single prediction or something, what we're going to do is have a sequence of tokens which are going to be the outputs. What are some important things to note here? One thing to note is when we feed in the input here, we're not just going to put a sentence, where we're going to put maybe, we're going to put, first of all, a special token at the beginning. So like kind of the first word of our sentence is going to tell us what type of task we're trying to do. So for example, the CLS token you see here, that means we're going to do a classification task. And we're going to feed in multiple inputs. So for example, when we're doing the training, we could have, say, a sentence and then a separator and then another sentence. The reason this is useful is because when we're doing tasks in the end, we're going to have maybe something like we have a question and then a paragraph of text. For example, think back to, I'm sure you've done some standardized testing of some sort where there's a paragraph and you have to read it, and then there's some reading comprehension questions to make sure you understood what goes on in it. That's similar to what's going on here. Yeah, you kind of write the question here and then the paragraph comes later. So, okay, this falls into a very, so yeah, let me just sort of summarize that. The input is going to be a sort of classification symbol, and then there's going to be maybe multiple sequences which are fed in with a separator. This happens at both the pre-training and fine-tuning stages. So once again, I'm going to note that this falls into the same paradigm as we talked about with GPT, where there are going to be two phases, one of which is going to be the pre-training, which is going to just take a lot of unsupervised data, and then we do some sort of fine-tuning at the end to really specialize for a task. This is basically, like I said, what all large language models do right now. They fall into the same type of paradigm. So, okay, this is kind of how well, hopefully this gives you a high-level picture of it. Now, what do we do? How do we train this? Because before, we kind of had this idea of how we did this like next word prediction type task. But how are we going to do it here? How does the training work? Let's just talk about the pre-training, for example. Well, let me just note about the training is that you're going to, like I said, get you're going to get some output for each location here. And the way you can picture these outputs is they're somehow related to the inputs in some way. So for example, this first thing we just said, this is a special token, which is says we're going to do a classification task. So on the output, we're going to have some symbol, the output here will give us some sort of representation of the answer to the overall task. So this kind of going, the result here is going to be a sentence level or a sequence level representation, kind of summarizes the sequence in some way. Whereas on the other hand, each of these things at each of the tokens, they're going to tell us something about the corresponding tokens. So there's kind of two types of information: token level information, which are kind of word level information, and then sentence level information. So we're going to train both of these token level and sentence level in order to learn different things. So first of all, the first thing we're going to do is we're going to talk about how to do the token level information. So how do we make it so that each of these tokens gives us information about what is going on at that token? And the way we're going to do this is kind of similar to what GPT did, in the sense that what we're going to do is we're going to try to make sure it learns how to basically fill in words which it didn't know. So before, remember, we built it up word by word, where given the previous of the sentence, Then you predict what the next word is. Well, here we're going to do something a little bit different. You can see here it's labeled as masked sentence A and masked sentence B. So what we do in these types of settings is we mask some words, and then we try to train the model in order to predict those words that we mask out. So for example, suppose our input, again, this is all going to be unsupervised in terms of the pre-training, but if you have something like, I suppose the sentence whatever the input is going to be transformed into this. So the idea is we're going to put these mask symbols into a regular sentence wherever at random places. So this is the input, and what the model should, in the pre-training stage, what we're going to do is try to train it so that it takes the sentence and will manage to output the sentence with the correct word filled in. So I took my dog for a walk. Right, so the main thing to get from this is that it's learning. If you have, sorry, let me just sort of summarize what's going on here. It's going to, what you're going to do with your training data set is you're going to start with your training data set, which looks something like normal sentences. You are going to randomly put mask characters into the into your training data, maybe at like 10% of the locations. And you're going to train your model, you're going to pre-train your model in order to predict what the right words are in these sequences. And that's kind of similar to the next word prediction, except it's kind of looking from all directions. It has both the things before and after in the sentence. So that is the idea. That's how we'll learn the token level representations. It kind of figures out how to fill in each individual token. But the other thing we're going to do is we're going to try to figure out representations of the overall sentence. And this is with something like what's known as next sentence prediction. So the idea is what we're going to do is we're going to take a bunch of pairs of sentences, and either where A follows A and B are sequential, or B is just totally random and unrelated to A. And the idea is that the network has to learn to predict whether B follows A or not. So, okay, let me sort of summarize this. So feed in sentences A and B. Either B follows A or is random. And yeah, we wanted to learn to predict which. So yeah, this is kind of, to give you an example, like going back to this, you could imagine that if our two sentences were I took my dog for a walk and then we played fetch at when we were out, those would be reasonable sentences to follow each other, and therefore maybe you should have next sentence prediction say yes, this sentence follows it. Otherwise you could have say sentence A being I took my dog for a walk, and the next sentence is I failed my test. These probably don't follow each other, so it should predict that's not the next sentence. So the purpose of this is trying to figure out more global level information about the sentence rather than just filling in these blank words, which kind of gives more token level information. So the idea is corresponding to each of these two different types of pre-training goals, that is filling in these masked words, the masked word prediction, and predicting whether it's the next sentence or not. Those are two different loss functions. Then we just sum the two losses. And yeah, that's kind of how we do the pre-training. All right, so that's kind of what's going on with BERT. Yeah, I'm not going to get too much into the fine tuning, but it's not too complicated. It's kind of similar to what you already know. The question is, how does it work? And I will show you this table from this from their paper, the BERT paper. This came out slightly after the GPT-1 paper. And you can see, first of all, BERT base, it seems like it don't worry too much about what these numbers mean, but BERT base, which is about the same size as GPT, it seemed to perform non-trivially better, non-negligibly better. These are significant advances in pretty much every task. But more significantly, this is a kind of important thing which alludes to a previous theme we've seen, which is that as you make it bigger, so BERT large has about 3 times the number of parameters as the other one, as BERT base, and you can see that it significantly improves as you increase the size. So once again, it seems that a bigger architecture only helps and manages to do a lot better, even even though they're kind of doing the same thing, maybe we just stacked some more layers and that caused it to be better. So this is going to be a trend, including the next 2 architectures I'm going to tell you about. So the next 2 architectures, we're going to go over them, the next one pretty quickly, just because it's kind of just the same story. But the next one is GPT-2, which is Generative Pre-training 2, the sequel. And this scales up quite a bit. This is 10x bigger than GPT-1. Maybe it's just called GPT, I don't know. But we call it GPT-1. So this is much bigger. I'm not going to spend too much time on this, but let me just show you how things scale up. So this is one task known as children's book test. Don't worry too much about what it is. But yeah, just to show you that this over here, basically on the left-hand side, this is GPT, this number of parameters. And this over here is GPT-2. And you can see as you increase the number of parameters from this to this, which is a factor of 10, but you can see how the accuracy generally increases from what I think this is the previous state of the art, but you can see that it improves significantly and gets relatively close to human level performance on various different tasks. So this is quite interesting, and essentially what it showed was this is again pretty much the same thing as what we did with GPT-1. It's just much bigger, scaled up. Yeah, so that's GPT-2. I'm not going to spend too much time on this because we're going to move on to the next and final one that we're going to talk about today, which is GPT, you guessed it, 3. So GPT-3 is essentially, once again, just making it even bigger and still reaping more benefits. So let me show you some of the I'll show you kind of what happens in terms of performance. But perhaps one of the more important conceptual things that happens with GPT-3 is that it kind of learns how to do different tasks without even requiring too much information. So for now, let's take a look at this picture. This is from their paper, from the GPT-3 paper. This is what you see on the right is fine-tuning, which is kind of how things have gone so far, all the things we've talked about. What we do is we first do some sort of unsupervised pre-training, and then given some examples, for example, this is like English to French translation, you can see that given some examples of what it looks like, then you feed it in, you do some gradient update, and then you get another example, you do gradient update, and so on. And then eventually you do a bunch of gradient updates, and then you just can ask a prompt, that is, you're saying, okay, translate cheese, and then it should predict fromage. So this is again what we've seen so far, and this is nice and powerful. The problem is that it can be costly, in the sense that doing gradient updates can be kind of expensive. First of all, it's not something you can necessarily do in every setting. For example, imagine you're at a hospital, you don't have access to a bunch of GPUs, maybe doing this fine-tuning training is kind of difficult, so it's not really quite as portable, stuff like that. So if you want to, and it requires a little bit more expertise to do too. So fine-tuning is great if you're a machine learning person, but it's kind of a little bit costly in various ways. But if you really want to get the best accuracy and stuff like that, then this is the way to go. However, the question is, can we do something even better than, not better than this, but kind of just different? And this is, I think, where some of the most surprising power out of language models comes from. And that is kind of what happened if you essentially just skip this fine-tuning phase. You just make the network do what you want it to do, which sounds almost magical. So let me give you an example. Imagine you do this massive amount of generative pre-training, the GPT procedure, the pre-training, which is on unsupervised data. You just basically teach the model what English is, and then you ask it something very simple, which is known as, this is a zero-shot setting. You just say, translate English to French, cheese. And that's it. You never told it anything about French besides what it may have picked up in its pre-training. You don't give it any examples of how to translate from English to French. You don't tell it anything more. You just write in plain English, translate English to French. And then somehow, magically, it seems like it can do this task often. This is known as the zero-shot setting, where you don't give any examples of what you're trying to do. You just tell it in plain English. And miraculously, it seems like these large language models can actually do pretty well at this sort of thing. So that's the zero-shot setting. The one-shot setting is you give it one example. So you say, okay, let's translate from English to French. You do all the, first of all, you do all the pre-training. You do translate English to French. Then you give an example of what an English to French translation looks like. The otter to l'outre de mer. And then you tell it cheese, and then somehow it'll be able to predict fromage, hopefully. So this is kind of interesting because it's just kind of prompting it and saying that, like, okay, this is what an English to French translation looks like, but you never told it what cheese is in particular in French, so it still has to just figure that out. And then there's the few shot setting, where maybe it's kind of like the generalization of the one shot setting, where you give it a few examples of what an English to French translation looks like, and again, it will translate from English to French. But the main difference between the things on the left and the right here is this fine-tuning involves gradient updates, whereas the things on the left, this is all just what you put in as your sequence. Think about, like, this is just the sequence that you feed in. Like this is x1 through xn are all these words here. The idea is that it somehow manages to figure these out even though you don't do any updates. So yeah, that is quite powerful. And I personally was surprised when I first saw these, in the sense that it's surprising to me that it could do that without any sort of gradient updates. It could just figure out how to specialize for each task without doing any sort of gradient updates. And it works surprisingly powerfully. And let me show you another plot from their paper. The previous picture was from their paper. So this is kind of where this huge scaling comes in. So what you can see here is a plot which shows that some task, don't worry too much about what the task is. It's not too important, but you can see kind of how I'll point out the trends that I want to emphasize. So the y-axis is how accurate the model is doing on this task, so higher the better. And what the x-axis is how many examples we gave. So for example, this leftmost one is saying the zero-shot setting. Remember, you just say translate English to French and give it the word cheese. This will be where the one-shot setting, where you give it just one example. And this is when you do, say, like 10 examples or 100 examples maybe. So this is the few-shot setting, where you have more than one, but not that many. Just feed it in rather than doing any sort of gradient updates. So, okay, these are all in no gradient update settings. And you can see down here, this is roughly GPT-2. And you can see that this is abysmal at this task. Like, it can kind of do something, but not very well. Yeah, barely any accuracy, even when you give it a bunch of examples with the context, in the context, and yeah, if you don't do gradient updates, it doesn't work well at all. If you increase this by a factor of 10 in terms of size, it starts getting okay, not like, I don't know, still not great. 20% of this task, is that even good? I don't know. But it starts doing something. But the most amazing thing is not if you multiply by 10 times, if you multiply by 100 times, then this 100 times thing, this is GPT-3 here, so you can see how much bigger than the previous one it is. GPT-3 is 100 times bigger, and you can see that, first of all, it can do still pretty bad, not that great for zero shot, but just one shot with an appropriate prompt cause it to jump to be much, much better than we saw in any of the other models. And then as you give more and more examples, it can be like 3 to 5 times better than anything else that we've seen. So this really shows the power of size in these language models, that somehow the bigger you make it, the more powerful it is, and can just do better. It's not like we're feeding it much more data or anything. It's just making the model bigger so it can learn better. It kind of seems like somehow the size of the model is the limiting factor here, rather than the amount of data, which is not true for other tasks in more difficult settings. For example, when we're doing, say, robotics, sometimes the data set sizes are the limiting factor there, just because it's not as easy to run a robot many times. But English, we have tons of English on the internet, as well as many other languages. So of course this comes at a cost, in the sense that this is a huge model. It takes a very long time to train, a lot of resources. So there's estimates of how much this costs to train GPT-3, which range from the hundreds of thousands to the millions of dollars just to train. Nobody really knows, and it depends on how you compute it, for example. But yeah, it's the short answer. That takes a very long time to train, costs a lot of money to train. In terms of, how do I mean a lot of money? It means in terms of like the amount of compute resource if you do this on a cluster or something, but also maybe you just convert how much time to money, and that kind of comes up as a cost. But besides that, also there's the one example in the paper, the GPT-3 paper, where they say that they found a bug, actually a minor bug in the training procedure, not something that could totally ruin it, but it could work better if they'd fixed it. But they discovered it too late, and the model was already training, and they didn't have, it would be too expensive for them to stop the training and fix the bug and run it again. So yeah, this is a lot more powerful, but it comes at a cost. So yeah, this is not the end of the line. There's been like more recent models. GPT-3 is kind of the most powerful large language model trained so far, but there's been things which have been trained with over 1 trillion parameters, so 5 times still this. So we'll see where this goes over the next couple of years. Yeah, as one last thing I could show you more plots on here are the scores on how it does on various different tasks. But let me just instead show you this kind of, we've seen enough of that. So let me show you this, which I think is kind of, one thing that these are very good at is in uncannily good writing of English, just producing text. For example, this was the context window. So, okay, let me note that the GPT-3, all the experiments they have in the paper are done in the few shot setting. That is, they don't do any experiments with fine tuning or gradient updates at all. I've seen other papers which do these type of updates, but it's very computationally expensive to do even fine tuning. You need something like dozens of GPUs just to do fine tuning. I think you need dozens of GPUs even just to run the model, but if you want to do fine tuning, you need many more. But anyway, the point is that they just fed in this context, and this context is a couple poems. So this is by a famous Greek poet, and it's translated into English. And it was also given in the context another poem by John Ashbery. And then the context, that is the input that was given, just ends saying Shadows on the Way by Wallace Stevens. So this is just giving a title and an author. And it's up to GPT to come up with a poem. And here are just 4 uncherry picked. So often experimental results are cherry picked to make it look as good as possible. But these are allegedly not cherry picked. So these are just 4 poems which it came up with. And if you look at them, they seem to be reasonable poems which could have this title. So it seems that this is just such a powerful language model. It can actually produce text which looks rather realistic. And I think I showed you earlier that, for example, like you can write news articles just by giving a title and maybe some important lines, and it'll come up with a nice story to go along with it. So yeah, just to sort of conclude, we've gone a long way from where we started, which is just attention. It seems that attention is a new mechanism and a new part of neural networks, which has given us the ability to do really unprecedented levels of power in large language models, as well as people are recently exploring attention for other tasks. But I think really that these large language models are kind of the killer app. So it's very exciting to see where we're going to go from here in terms of improving things further.